Great. It's a pleasure having you here today for this webinar of the Technical Talks of CTSoc series. Fabrizio Lamberti, I'm Vice President of Technical Activities for CTSoc, and just to tell you what the agenda for today, I will give a brief presentation of what the technical activities of CTSoc, of IEEE Consumer Technologies are, and then I will move quickly to introducing the Technical Talk series, and then leave the floor to the colleagues, the officers of the TCs and our speakers for today's webinar. The total duration is expected to be 1 hour. The technical activities areas is one of the areas of CTSoc together with conferences, publication, educational activities, standards, industry, history. And basically, the technical activities areas is in charge of managing the technical aspects in the field of interest of IEEE Consumer Technology Society. It includes basically the Future Directions Committee and the technical committees itself. If you want to get more information about these areas, you can go on the main website of CTSoc and check the technical activities tab. As I said, we do have 15 technical committees established so far. As you can see, they are covering all the areas of interest for the consumer electronics and consumer technology domain. And today we do have two speakers which are representing the machine learning, deep learning, and AI in consumer electronics, the MDA+CSH and the CSHTC, which is the acronym of Consumer System for Health Care and Well-being. The structure, the organization of these technical activities areas is this one, and within this organization, the technical committee board is coordinating the activities, and in the board we have myself acting as VP Technical Activities and Board Chair. We have the Vice Chair, Dixon Lin. We have the President, Fabrice Labeau, VP Conferences, Fauzi Beman, VP Publication, Norbert Eringsar, VP Industry and Standard, Michael Kondrik, plus the officers of the 15 technical committees. Here you have their names in case you are not yet a member and you want to contact them. Each TC it's covering one of these aggregate sub areas, and they have a mission stated in their webpage. They have a list of members. They have periodic meetings. They have minutes of the meeting. And if you are not a member yet, there is a way for joining. And what is interesting to point out is that you don't need to be an IEEE or a CTSoc paying member in order to be a member of our technical committee. So this is a way to bring a growing community of people in the field of interest of our society. So here you have the QR code, link, and please feel free to share with your colleagues who want to get involved. The community is growing. This community is only partly overlapping with the list of members. These are people who really want to get involved in the activities. And why getting involved in the activities? Well, because the technical committees have been launched with a goal of supporting the technical activities in all the other areas like conferences, publications, standard education, and history. So they are there to investigate, evaluate, foster current and emerging technologies in the application in the field of interest of CTSoc, and new TCs can be created. They should support the development of new initiatives. They should define new areas in the field of interest of CTSoc. And some examples of the opportunities that have offered and have been offered to our technical committee members are to serve in technical positions of our conferences, both the flagships and the vertical and topical ones, being selected for associate editor positions. By the way, the selection for the associate editor of consumer electronic magazines in process, um, be allowed to organize special sections in journals, but also be selected for organizing workshops and sessions in conferences, to get involved in other initiatives which CTSoc is contributing to, like the IEEE digital reality, the digital privacy, etc. We also launched collaborations with other societies in IEEE and outside IEEE. The technical committees are launching special interest groups. One is being created on the metaverse, but from time to time there are calls for distinguished lecturers which are paid to or allowed to travel and spread the word into IEEE CTSoc chapters and stuff like that. They are selected also through technical committee members. We launched last year funded projects like student internships. We have been involved in the implementation development of standards with other associations like MPI and IEEE as well. So that's it. And regarding opportunities offered, we are looking for contributors like reviewers, track chairs, or authors for our conferences. And I take the opportunity of this moment to share with you CTSoc conferences which have call for papers open so far, and this will be also a place, an opportunity for meeting you. So please check out these conferences and consider submitting. But finally, about journals, for instance, I mentioned it already, our two flagship publications, IEEE Transactions on Consumer Electronics and IEEE Consumer Electronic Magazines. They have call for papers and call for special issues, and also call for special issues proposals. So please check this page on CTSoc website tab publications. Okay, and reaching finally the topic of today webinar, technical talks of CTSoc. So the technical talks have been started as an initiative of individual TCs, which has been clustered into a technical activities areas initiative. And we have this webinar every 1 or 2 months. So the next webinar will be end of March, beginning of April. So the details will be published soon. But today we are here because we are going to attend and participate at the 20th webinar of the series. And we'll have two speakers from, as I said, from the MDA and from CSHTC. So I really want to thank Mr. Matthew Scott from Mindset AI and Professor Mohamed Abdur Rahman from University of Prince Muqrin, Saudi Arabia. You can read here the title of their speeches, but now I will leave the floor to the officers of the two TCs. So first, the MDA TC, Paolo Napoletano, who will introduce the speakers. So thanks to the officers, thanks to our speakers, and thanks to all of you for attending today's meeting.
Thanks, Fabrizio, and dear all. I'm very honored to introduce today to this technical talk our colleague Matthew Scott. He's more than 20 years of experience in AI and machine learning research and development, and spanning Microsoft research and venture-backed research-driven startups. He currently serves as a co-founder and CTO of Mindset, and is an inventor of more than 100 granted and pending AI ML patents, and has received over 10,000 citations in peer-reviewed publications. He has received multiple research honors, including a Best Paper Award and a Best Paper nomination at CVPR and ICCB, along with additional technology awards from Microsoft Research and Google Research. He has led the development of AI ML-driven products used by more than 100 million consumers worldwide across multiple Fortune 500 companies. Matthew currently serves as chair of the IEEE Industry Engagement Committee, co-chair of an AI Technical Activity Board and ad hoc committee, member of the MDA, I'm chair of this technical committee, and of the IEEE Consumer Technology Society, and he is associate editor of IEEE Access, handling AI and ML topics. So Matthew today will give you a talk titled LLM Optimization for Mobile AI, Methods and Research Frontiers, from billion parameters models to on-device intelligence. So Matthew, the floor is yours, and now it's your moment. Thank you.
Perfect. Thank you so much. Before I begin, just a thumbs up if you can see my screen.
Perfectly.
Excellent, excellent. Well, let's get started. So good morning, good afternoon, good evening, wherever you are in the world. Thank you so much for the introduction. I'm Matt. I will talk to you today about, I think, one of the most consequential challenges in applied AI right now for consumer devices, or consumer technologies. How do we take large language models, which are extraordinarily capable, but extraordinarily large, and make them run efficiently on the consumer grade mobile devices that billions of people carry in their pockets? So this is not just an engineering convenience problem. This is something that touches privacy, latency, accessibility, energy consumption, and ultimately determines, who gets the benefit really locally from the LLM revolution. And so over the next 20 or so minutes, I will walk you through the methods, the state of the art, and where the research frontiers lie. And so let's get started. Here's the roadmap for the talk. We'll start by framing what the problem is, which is, in summary, the gap between what the frontier LLMs need and what the mobile hardware can deliver. And then we'll talk through the 4 core optimization techniques one by one, with a detailed comparison of the quantization methods that matter most, practically speaking. And from there, we'll look at the architecture level approaches like MOE, as you know, mixture of experts, and mobile first model designs. And I'll survey the deployment runtime landscape as it stands right now, early 2026, and discuss how these techniques combine in hybrid strategies for practical deployment. And then I'll touch a little bit on the sustainability angle, which I think is underappreciated, and lay out a practical 6-stage pipeline and close out with the open research problems where I think the most impactful work remains to be done. So without further ado, let us proceed. Okay, the problem. Let me put the scale of the problem in concrete terms. Rumor has it, not just rumor, but a lot of people estimate the GPT-4 level model, so that kind of class of model, is estimated at over 1.8 trillion parameters. So at FP16, the floating point 16, that's over 3 TB, 3 terabytes, just for the weights of the model, not counting activations or KV cache. On the right-hand side, you can see what we have to work with. Say an iPhone 16 Pro has 8 GB of unified memory, and that's shared with the OS and every other app. Even the Pixel Pro 9, it has 16 gigs. That gives you maybe 6 to 8 gigs of usable headroom. Our practical target for a smooth on-device experience is really just under 4 gigabytes for the model. Now, here's the key technical insight. The LLM inference during the decode phase is fundamentally memory bandwidth bound. Every single token you generate requires streaming the entire model's weights through the memory bus. So this isn't just like, does it fit problem? It's a throughput problem. Smaller models directly translate to faster token generation, which is what the user actually perceives as a good user experience. And then you have the privacy argument and the offline argument. Many users, enterprise, healthcare, government, they simply cannot send their data to a cloud endpoint. On device, for those users, is the only option. So optimization isn't optional for many use cases. It's a gating factor on whether LLMs can reach many scenarios at all. So before we go deep on any one particular method, let me give you the high-level map. There's 4 main pillars for LLM optimization. And in practice, the most successful deployments combine at least two of them, two or more of them. Many of us know about quantization. Quantization is the workhorse. It's really a fundamental aspect of reducing the numerical precision of weights and activations. You go from, say, FP16, which I mentioned earlier, to int4, and that alone gives you 4 times the memory reduction. It's the single most impactful lever, and the one with the most mature tooling is the quantization workhorse. Pruning is the second one. I'm sorry? Okay. Pruning removes the second one. Pruning removes the redundant parts of the model, the individual weights in the unstructured case or entire attention heads and layers in the structured case. So the reduction factors can vary widely depending on how aggressive you want to go, but 2 to 10x is typical. Knowledge distillation, the third pillar, is fundamentally different. You train and this is in the news recently on distillation, but it is a very good research technique. You train a smaller model, we call it a student model, to replicate the behavior of a larger model, teacher model, we call it. This is how models like Tiny Llama or Gemma 3 at 270 million parameters were created. The compression ratios can be enormous, 5 to 50x, but it requires a training pipeline. And then the last but not least is what we call the low-rank methods, particularly LoRa or QLoRa. They factorize the weight matrices into smaller components. These are especially popular for efficient fine-tuning, but also they do contribute to compression. And so you can see the little orange boxes at the bottom. These are the typical reduction factors. And so in the next few slides, I'll go a bit deeper on each of these, and I'll start with quantization. But again, as a summary, many practitioners, they will use one or more of these techniques combined, and that will get you a lot of progress. So let's dive in on quantization, the first pillar. Quantization is where most of the practitioners start, and for good reason. It's the fastest path from a research model to something that runs on your phone, to the consumer device. And the two main approaches are post-training quantization, or PTQ, and quantization aware training, QAT. So PTQ, the first one, is the practical, pragmatic choice. You take a pre-trained model, you quantize its weights, and you're done. No retraining needed. Simple and done. The QAT bakes quantization into the training loop. It's more sophisticated, which can recover a bit more accuracy, but it requires more compute budget. So there's a trade-off. So what most people believe is there's this sweet spot. The sweet spot is for on-device LMs is the int4, 4-bit integer weights. This gives you roughly 4 times the memory reduction compared to the FP16. And for models that say 3 billion parameters and above, the quality retention is pretty good. But going from FP16 to int8 is safer. It's less than 1% what we call perplexity increase on the standard benchmarks. But the 2x reduction often isn't enough for mobile. It's too big. So the frontier right now in the research is what we call ultra low bit quantization. Usually it's 2 to 3 bits. Where I'm from, my original lab, Microsoft Research Asia, we have something called BitNet. You may have heard of. That's even lower than this, but it's more advanced in the research. But where people mostly lie in ultra low bit quantization, 2 to 3 bits. A lot of recent work has been done here. The idea is that not all the weights, this is the key insight, not all the weights in the model are equally important. So you can identify the critical weight groups and just retrain those at higher precision while you aggressively quantize the rest. So one thing I want to highlight that's often overlooked is the KV cache quantization. So we know about, in large language models, KV cache, quantizing the KV cache, key value cache. For long context applications, which are increasingly common, the KV cache can dominate the memory usage, even more so than the model weights themselves. So recent work shows that you can quantize the KV cache down to 3 bits with just negligible quality loss. And this is often the difference between a model fitting on your device or not. So let's now do a little bit of a comparison. Compare the 3 major quantization methods that if you're a practitioner, you'll often see. So this is the question I'm often guessed is given is which one should I choose? I have all these different options. I would say, well, let's go through them. GPTQ uses this, what we call layer-wise second order approach. It's a method that accounts for curvature of the loss landscape when deciding how to round the weights. It's one of the first practical LLM quantization methods, and it works well. But at 4-bit, it retains about 90% of the original model quality. The inference speeds you see here is quite good, 276 tokens per second baseline, jumping to 712. This shows how important the runtime kernel is on top of the quantization method itself. AWQ is another great one. Activation aware weight quantization. Again, it takes a different approach. It scales weights based on which ones matter the most to the activations, not just the ones weights in isolation. This gives you about 95% quality retention at 4-bit, which is, I would say, meaningfully better than GPTQ. There's really no point of having an LLM run on your phone if it's not good quality. And I would say that this one is really designed with edge deployment in mind. A lot of people in the community, they know about Llama CPP if they want to run locally. And you have these GGUFs. It's the most practical, pragmatic option for mobile, I would say. It's format agnostic. A lot of people share them on Hugging Face, this website. How it actually works is uses our classic k-means and rounds to the nearest approaches. And crucially, it's CPU friendly. You don't need a GPU kernel. It can run on almost anything, which makes it really a go-to for cross-platform mobile deployment. A note on the inference speed numbers, these were measured on an A100 GPU, so they don't take into account the mobile numbers. On the mobile, you'll typically look at single-digit to low double-digit tokens per second, depending on the model size and device. The relative rankings hold, relatively speaking. Bottom line, if you need maximum quality, I suggest go with AWQ. If you need maximum portability, I suggest go with GGUF. And I would say GPTQ, the first one, sits in between and is most useful for if you have a GPU-backed scenario or batch scenario. Let's go on to the second pillar that I discussed earlier, we call pruning. There's two fundamental flavors, I would say, that have different practical implications. The first one, unstructured pruning, zeroes out the individual weights scattered throughout the attention and feed-forward layers in the model. You can achieve really extremely high sparsity. 90% or more of the weights can just be zero, and the thing still works. Tools like Sparse GPT, you may have heard of, or Wanda, can do this in a single shot without any retraining. This is really practical advantage, but there's always a trade-off. The catch is that you need hardware or kernels that can exploit the sparsity to see a speed up. On today's mobile, mobile phones have, sometimes we call NPUs, but there's also GPUs. The sparse optimizations, they don't really work very well yet. You often don't get the latency benefit you'd expect. This is improving, but it's not fully there yet. The structured pruning, I would say, is the more mobile-friendly approach, structured pruning. Here, you remove the entire attention heads, the feed-forward neurons, or even the complete transformer layers. The beauty is that the resulting model is what we call a standard dense model. It runs on any hardware with no special parse support needed. You get the direct reductions in compute, memory, and latency. I want to point out one of the projects here called Mosaic, was published recently, is one of the more interesting, recent methods, if I would suggest you can look into. It uses composite projection pruning. Essentially, it identifies which structural components contribute least to the model's output and removes them in a more principled way. There's also something called LLM pruner and short GGP. I will actually also link some papers at the end of my talk if you want to do further investigation. These are notable structured approaches that work well in task-agnostic manners. This talk is we also call it research frontier. So I will make a little note on a research frontier I want to highlight. There's many, but I want to highlight one at the bottom. We call it fine-tuning free pruning. If you can prune an LLM without any retraining, you can apply it to every new model release immediately. And that's a practical gap that is being closed right now. So this slide is the distillation low-rank methods. This is the third pillar. These are two complementary strategies I've grouped together because they both operate at the training or fine-tuning stage rather than the post hoc compression. Knowledge distillation for LLMs really has evolved beyond the classic soft logic transfer from the original Hinton paper, if you're familiar with that. Modern LLM distillation also transfers chain of thought reasoning, patterns, and instruction following behavior. The student in the student-teacher model doesn't just learn to mimic the teacher's output probability, it learns to reason similarly. That's a key point. It thinks like the teacher. And so it's not just a sort of a cheap copy. It actually can have some fundamental capabilities, even at a smaller size. The production successes here, I think, are pretty notable. Again, I would look into Tiny Llama Gamma 3. They are 270 million to 1 billion parameters, 5.3, 5.4, mini. These are all techniques that relied on distillation from much larger teachers. These models punch well above their weight class because they inherit the reasoning patterns that the models of 10 times, 100 times, their size. So this is a really powerful approach. The CQKD framework, which I want to highlight here, it's from last year, but I want to say it's worth taking a look at because it demonstrates the power of these unifying techniques. You run the unstructured pruning, cluster-based weight quantization, distillation in a single training loop. And this achieves tremendous compression factors, can be over 1,000x compression factor, extraordinary. So look into the CQKD. On the low rank side, LoRa, QLoRa, which many of us use, have become the standard for efficient LLM fine-tuning. The key insight here is that the weight updates during fine-tuning are low rank, but you can decompose them into much smaller matrices with minimal quality loss. QLoRa takes this a bit further, quantizing the base model to 4-bit and only keeping the LoRa adapters at the higher precision. So this is how finally people fine-tune these massive multi-billion, say 60+ billion parameter models onto a single GPU, and something that would otherwise require multi-node cluster, multiple GPUs. But we're talking about mobile. So for mobile, these methods matter because they let you create specialized smaller models efficiently for the consumer technology. A domain-adapted 1B, 1 billion parameter model can outperform a generic 7B model on your specific task. And getting that on your phone is a tremendous benefit for the consumer. So let's just zoom out for a second here from the individual compression techniques. And I want to look now at architecture level decisions. When you're going about building models or leveraging models, you want to consider the architecture before you even start to compress things. So many people know recently that MOEs have become quite popular since last year. MOEs, they're called mixture of experts. They became really the dominant architecture for frontier LLMs. I'd say over 60% of major model releases since early last year, have adopted MOE. Most of the new releases are MOE. Why? The appeal is really obvious. There's sparse computation, means that only a fraction of the experts are active for any given token. So you get the capacity of a much larger model at the compute cost of a smaller one. So it's really, really strong. But there's always a trade-off. So for the mobile issue, the mobile catch is that despite having sparse computation, you still need all the experts loaded in the memory. So at 47 billion parameters, the MOE model with 8 experts, you still need 47 billion parameters in RAM, even if you only use the 2 experts firing per token. So this makes the memory versus compute disconnect tricky on mobile, although there's some new techniques being developed that leverage the disk to kind of work in concert with the memory. This is one of the tricky parts of MOE. So there's been some projects like Mobile from 2025. They have an interesting solution called the big little expert strategy. For the tokens that the router thinks is unimportant, it routes to a smaller, cheaper model, cheaper experts. For tokens that really matter, it uses the full size experts. And this reduces the total memory footprint while preserving the quality where it counts. On the right-hand side, I would say this is the mobile-first LLM architectures. So I would say this is seeing a convergence on mobile-first approaches. There's a breakthrough here, really, in terms of insight over the last 2 years, is that the sub-billion parameter models, really small models, can handle many practical tasks that require, that used to require 7 billion or more. So I would highlight like Llama 3.2 at 1B and 3B. Gamma 3 down to 270 million parameters, 5.3 mini, 5.4 mini. These are purpose-built for edge deployment. And the architectural innovations, I think, like grouped query attention and sliding window attention, directly reduce the per token compute and memory requirements. These aren't compression techniques applied after the fact. They're efficiency really baked into the architecture from the day one. So where are we now in terms of the landscape, the device landscape of on-device LM deployment landscape? Here's how it's constantly changing. Over the last 18 months, first of all, this is not research anymore. This is practical work, and we're going to start to see more and more of this as the industry evolves. Meta has something called XUTorch. It hit the version 1.0 last year, late last year. It's significant. It signals some production readiness. It supports both iOS and Android. It handles the transformer-specific graph optimizations and has really first-class support for quantized models. Llama CPP, the GGUF ecosystem, remains the most portable option. It's CPU first, which means it works on essentially any hardware, regardless of the GPU or NPU availability. For prototyping and broad device coverage, I'd say this is hard to beat. Google has their LM inference API called MediaPipe. It provides a really good solution for Android. You just point it at a model, configure the GPU, delegate, and have an on-device inference. Apple has Core ML. It has a native transformer graph optimization system that allows you to run on their neural engine. So the recent iPhones, when you're purchasing iPhone, it says AI, can be supported. They're talking about the neural engine, and you get this hardware acceleration essentially for free if your model is in the right format. I just want to emphasize 2 technical points. First, the KV cache, the key value cache compression, is often more impactful than the weight quantization for long context applications. If your use case involves summarizing documents or multi-turn chat with a long history, you need to optimize the cache, not just the weights. The second, the fundamental bottleneck, again, remains the memory bandwidth, not just the memory bandwidth. On the mobile SoCs, the memory bandwidth determines how fast you can stream the weights during the decode process, and that directly caps your tokens per second. So every byte you shave off the model through compression translates to faster generation. This is why compression isn't just about fitting the model, it's about making it actually usable. Because yes, I can fit the model on the phone, but if it's 2 tokens a second, it's not going to be a great user experience. So you have to think of more than just the raw compression. So let's talk about practical deployment. As I mentioned before, most practitioners leverage multiple methods, combine them together, we stack them. So you almost never just use one optimization. The gain is really bringing multiple together in a principled way. So you combine the quantization, say pruning, distillation, you can achieve 95% total size reduction. The CQKD pipeline I mentioned earlier is a really good example. This is something that can be used to reduce the precision, then distillation to recover any lost quality in a single loop. The layer-wise mixed precision is a practical technique that deserves more attention. But I do want to be cognizant of time, so I won't go into too much more detail on that. Let me say just one last thing that I think is important, is a runtime adaptation. It's a frontier method. Imagine the device dynamically adjusting the model's precision or sparsity based on whether the phone is actually plugged in on battery. So energy use related to how it actually processes the model. If it's on battery, it goes a different path, and it may consider thermal throttling, even based on the complexity of the user's request. So simple queries get the lightweight path, complex reasoning gets a full model. So I think this is where the field is heading on mobile deployment, is considering the actual state of the phone itself in the running of the model. I think that's quite interesting. I don't want to say too much on this, but there is something we should say about the environment. There is an impact when we're having smaller models. There's more carbon efficient LLM inference when we're not, consuming so much energy. I think that's an important thing to say here, but I don't want to harp on it because we're running low on time. I do have a multi-stage pipeline I wanted to lay out here. I'll just speak to it rather quickly. This is if you're a practitioner. I want to just give you a practical baseline from this talk. I want you to get something out of this talk, how you can go from start to finish. And there's a multi-stage process. Select your base LLM is a design decision. Match the model family, size, and task complexity to your problem. For example, if you're doing a summarization task on a flagship phone, you may want a 3B model. A simple classification task, may need something smaller like a 270 million parameter model. Stage 2, distill or pre-train on a compact student model from a teacher frontier model. So that's the distillation technique. Then stage 3, you want to prune, remove the redundant attention heads. Stage 4, quantize. Stage 5, and this is where many teams have trouble on stage 5, is you want to profile and optimize the actual target hardware to really get the most out of the hardware. And stage 6 is deploy. Use the right runtime, the XUTorch, Llama CPP, Core ML if you're using Apple, etc. So the key insight from Apple's own practitioners is that this process is iterative and task specific. There's no universal recipe. So just profile early on real hardware. I know we're out of time, so I'm not going to harp on it, but there is these research frontiers. I mentioned the ultra low bit quantization, multimodal and device LLMs, and other techniques here that I think you can read on the screen. And so I don't want to go through each one because we're running low on time. So with that, I would like to say thank you so much. I do have, again, I did quite a few references for this talk, but the 3 I've listed here I think are really helpful. So if you want to look those up, you can get more information. And thank you so much for listening to my talk.
Thank you, Matthew. I think it's now time for questions.
Maybe for the sake of time, let me thank you, Paolo, again, and also Matthew for this great talk. I think it's really right in the central scope of CTSoc and what is really relevant today. I would move for the sake of time to the next speech and then leave time for question if there is time remaining, if it is okay with you, Paolo and Alessandro, of course. Okay, so in that case, Alessandro, please, you're free to introduce our next speaker. Sorry for not having called your name first, but I didn't recognize you from Asus. I wasn't sure you were the actual speaker. So, okay. Please, Alessandro, and
Thank
thank you,
you.
of course.
Thank you, Fabrizio, and thank you everybody for this opportunity. So the second speech of today's technical talk event is from Dr. Mohammed Abdurrahman, which is a full professor, current head of the Department of Cybersecurity and Forensic Computing at the College of Computer and Cyber Science of the University of Prince Muqrin in Medina, Saudi Arabia. Dr. Mohammed Abdurrahman has received the Best Research Award from UPM for 5 years in consecutive years and is among the world's top 2% scientists. He has received more than $15 million dollars research grants from funding bodies in the USA and Saudi Arabia. And his interests of research include self-explainable and trustworthy artificial intelligence, security at cloud, fog, and edge, adversarial attacks and defense mechanisms of AI models, IoT and 6G security, AI-assisted cybersecurity operations, security and privacy for consumer devices, and multi-agentic systems for consumer edge devices. So plenty of interesting topics, also in the light of the topics, or both topics of the technical talks of today. And notably, his presentation is about multi-agentic AI at the edge, securing cooperative agents in consumer IoT and smart environments. So, Dr. Abdur Rahman, the floor is yours, and thank you for your kind availability and in advance for your presentation. You are muted.
Can you hear me?
Yeah, loud and clear. Thank you.
Is my screen visible?
Yeah.
First of all, thank you very much from all over the places in the world. In this presentation, I will be talking about mostly security aspect of the most recent multi-agentic system, specifically for edge devices and in the healthcare perspective. First, I will introduce about the how multi-agentic system at the consumer edge is disrupting the world, and then some of the threat landscape we should be very careful about, because this talk is mostly about advisory, about our research on very state-of-the-art AI models, specifically agentic AI systems. I will also present some defense and mitigation strategies with takeaway messages. The rise of the multi-agentic AI. The first generation was about basic large language models, followed by RAG, and then the agentic LLM started. And here we are witnessing the multi-agentic system. Now, specifically the single large language model, which is very powerful, but it couldn't act. So it was limited to autonomy, memory, and the coordination. That has brought this agentic architecture, so that our agents, they can react to input and output. They can use existing language models, small or large. They can use existing services. At the same time, they can access the memory. So these agents are being empowered to actually do things. As an example, our previous colleague Matt, he was talking amazing about the whole effort is going on, how this can fit into the consumer side edge devices. This is an example, for example, a very recent model. I will basically use OpenClaw as an example in my reference. That, for example, this OpenClaw model has been very successful in both the small and large language models. It can even fit into a Raspberry Pi. Now, this multi-agentic shift, I would say, it allows autonomous goal-seeking agents that can reason, that can plan, that can communicate, and that can act either individually or as a team. Why it matters, basically. Why we have to worry about it, and we have to be very careful, because these agents can perform continuous autonomous operations. It can access APIs, it can access databases, it can access physical systems. So we have a real breakthrough in cyber defense, healthcare, and many other consumer applications. This is one example. I have taken it from OpenClaw architecture. Now, these multiple agents, or these agents, they can act as a personal assistant. They have access to the terminal, they can access file systems, they can email, they can access calendars, they can do planning, and they have permissions to do things, basically. And even they can access the emails, they can read emails, write emails, read WhatsApp messages. It's a fantastic world. in the healthcare perspective, think about how this multi-agentic system can add value once it has access to the LLMs, access to the file systems, access to processes. When a patient, for example, visits a hospital, and the patient goes through different processes, follow-up procedures, treatment plan, prescription, medical diagnosis, and things like that. So in every visit, a lot of these processes happen. Sorry. This actually brings the power of agentic automation. If we can fuse the multi-agentic systems that can do reasoning, that can read handwritten documents, that can have voice notes basically written in medical grade. So this is an endless opportunities for healthcare applications. So all these manual processes that requires automation actually can be addressed by multi-agentic AI system. That's the beauty that is basically in our table. So what is behind this AI ecosystem? I will quickly walk you through. At first, these agents can use existing LLMs as a brain. It can also decide, it can plan that what needs to be done. It can also access tools, for example, send email or whatever tool that we want it to access. Also, it can orchestrate. It can have a gateway to do all these activities that we want it to do. So what happens is that we can give it a big task. It can think using LLM. It can choose the right tools, and it can check whether the quality has been achieved and do this repetitive process. Think about in a medical healthcare application in a hospital, for example, that a hospital assistant is receiving hundreds of patient files every day. So it wants to read the files, do what has to be done with that file, and use the right tool. And all these manual processes happen basically. But then, thanks to the rise of this multi-agentic system, actually we have been using this quite some time. So we're seeing the value and the power of this multi-agentic system, how much it can automate just fractions of seconds that would take days or even weeks. Even we can automate some cron jobs that it can automate. For example, whenever any patient report comes, you should immediately do 1, 2, 3. So do these automated processes at that particular time, or that particular hook, or that particular, for example, trigger. So multi-agentic systems are very specialized to handle these situations in healthcare specifically. Now, given all these actual advancements, I want to start my main talk about the threat landscape. What is the risk? The risk is these multiple agents, they can coordinate, they can give tasks to each other. And so basically this amplifies the vulnerabilities. It can propagate malicious behavior, bypass human oversight if not properly secured. So that means the one compromised agent in the whole pipeline actually can poison the whole shared memory, manipulate tasks, or manipulate the goals, or it can even bias each other, one just compromised agent, so that it can lead to a coordinated deception across the whole system. So in other words, unless these multiple agents are being properly basically guardrailed, then the problem starts. Example, once these agents are given access to the shell, read-write files, messaging apps, third-party skills, we have to start counting the massive amount of security flaws that can be brought by this agentic system. This is just a few tips on the iceberg. For example, a file system access has risk, command execution because agents are allowed to do things. It can exfiltrate sensitive data. It can also do prompt injection, one of the most critical security flaw of the multi-agentic systems. This is an example. For example, a medical doctor wants to, for example, set up a calendar. So now this agents, if the agent is compromised, then the agent can not only do the job, but the agent can also exfiltrates the personally identifiable information as well. So leading to so the different layers of attack happens. It can be prompt and memory layer. It can be goal and planning layer. It can be coordination layer. It can be communication layer, or it can be execution layer. Very funny is that I was studying a research today from one of the top journals, is that most of the attack happens in the communication layer, as an example. This is thanks to WASP. So WASP is one of because this is the security basically community. WASP actually provides amazing direction, and so WASP has been very instrumental in releasing different guardrails, different advisories. So one of them is Mastro. So Mastro, basically, this is an example that how many different threats. This is a threat model. Mastro is a threat model that actually identifies different threats appearing in different layers of multi-agentic system. So I will not go into details, just wanted to tell you. One of the pillar of this automation process is MCP, Model Context Protocol, as an example, that is that empowers this multiple agents to coordinate. So this is a subset of the vulnerabilities that have been identified on MCP protocols. Since 2000, basically, so since 2024, I would say, more than 102 types of vulnerabilities have been reported by researchers of different types on multi-agentic systems. Now, I will point out some of the mitigation strategies, how we can safeguard. We cannot live without this, but we have to be careful. First of all, these risks of these agents have to be properly studied. I will not go details because this is core into cybersecurity domain, but I'm just pointing out that different very high-level cybersecurity aspects that we use in other domain, actually also some of them also applies to many new advisories are provided for securing the multiple AI agents, specifically the consumer-centric applications. This is a little bit drilled down inside. One of the attack is called prompt injection attack. So imagine that we have a new application that has stormed the society called OpenClaw or CloudBot or MaltBot, whatever we say. Now, these agents can be vulnerable because of the very highly disruptive code, everyday changes happening. So that's why they're very vulnerable. Also supply chain attack. So whenever there is any, for every type of attack, there should be a guardrail, whether, for example, the prompt should be validated. If there is a strong validation, then if there is a prompt injection, then it should be blocked. If it is not, then basically the malicious activities happen. Again, I'm just giving a reference to the OpenClaw because this is the most disruptive multi-agentic system I have ever seen. So basically, we have this has been studied by security community that for the reconnaissance, exploitation, different layers of attack that it happens. Basically, the mitigation strategies are also being developed by the security industry. This is, for example, some of the advisories that are provided for, because see, if you really want to look at the multi-agentic system of everything that you can think about, every aspect, basically it is embedded into this platform. That's the beauty. So we studied the security aspects, that how to secure this very famous OpenClaw framework. So it starts from external access, security boundary, then the gateway, secure gateway, then the secure agentic layer, and finally, since they access our file system, they access our precious critical infrastructure, so it has to be secured as well. So this security defense in depth has to be there. It starts from access control mechanism, network security, sandboxing, credential. Strong credentials, and also the monitoring framework. So multi-stage security has to be there to secure the multi-agentic system. Also, the traditional DevOps basically has to be updated to SecDevOps. Also, the different types of security and privacy testing has to be there. For example, ethical hacking, risk assessment, auditing and compliance test, pen testing, red, blue, purple teaming, security and vulnerability scanning, cyber threat intelligence, and privacy impact assessment. These are different strategies that has to be done to secure our multi-agentic system deployment for consumer applications, because human life is there. There are different amazing frameworks started appearing to safeguard our agentic AI system for consumer applications. Mastro threat modeling, I said, WASP security playbooks, I will share with you shortly, quickly. The blockchain community has done an excellent, fabulous, amazing job. I will show you quickly. For example, this is the Mastro. They provided 7 layers of security for multiple agentic systems if we want to apply it to our applications. If, for example, like any other application, we manage secure session, we have identity access management, same thing with multiple agency system. If you have 10 agents, they distributed the work and they divide the task for the master and slave. So how do each other know that yes, that the agent that they're communicating with is actually trustworthy? That's where the blockchain identity management is being proposed by ERC 8004, basically blockchain algorithm. So it can basically verify the agent identity, the reputation of the agents, and the every task that the agent are doing basically can be validated, similar to how blockchain actually validates. Also, more guardrails, for example, ethical, safe, trustworthy, and other. And at the same time, there are many security advisories are provided by the security researchers as a guardrail for multi-agentic system. For trust boundary, because we make sure that these multi-agents are trustworthy. That's why a lot of trust boundaries have to be applied on the input to the gateways, or how the agents are handling the language models, and also the output. So from all the way input to the output, this has to be guardrailed. Finally, if we are using MCP servers, because that's the heart and the foundation of this multiple agent, how they access basically tools. So it has to be also the secure. Also, if this is just one example that any new framework comes cannot be trustworthy. As an example, this OpenClaw, it can access, it can do amazing things, but actually the flow has to be verified with and should be checked, should be passed through authenticated layers of workflow, enterprise workflow, hospital workflow, or any enterprise that is using these multi-agentic system. Again, the WASP has provided different playbooks that enterprise security team can use to make sure that these tasks that are done or activities done by agents are basically trustworthy. Key takeaway message. These agents are basically disrupting the society. I have been personally using it, and the power that I see is just mind-blowing. This is really mind-blowing how much these multiple agents with the multi-agentic system can disrupt every society that we are talking about. However, this is bringing new layers of attack surface, from memory poisoning, goal hijacking, and inter-agent communication hijacking, man in the middle, rogue coordination. So security should be by design. Security should be by default of this type of embedding of this type of multi-agentic system. Different defense mechanisms have to be embedded. For example, I shared with you some of them: Mastro, WASP agentic playbooks, then using the blockchain for decentralized provenance and the trust mechanisms, so that either human or one agent can trust another agent. Finally, there should be some measurable resilience from red-blue emulation. Thank you very much. I will thank you for the IEEE CTSoc for giving this opportunity. Thank you very much. Thank you.
Alessandro, please.
Thank you, Mohammed, for your very interesting presentation and also to trying to stay on time. And Fabrizio, the floor is yours.
So again, thanks also to our second speaker. I think again there is a lot of the interest. What is very nice and fun is that there was an unexpected connection between the two speeches, which is not searched intentionally. So I think we are running out of time. So I would like to maybe ask if there are maybe one quick question for each of our speakers, if any. Otherwise, of course, we have their contacts and we can reach them out. Any question from the audience? I think it's not because lack of interest, but of course time constraints. Unfortunately, we need to move everyone to one call from one call to another. But anyway, please consider those who are not members. Please consider joining our technical activities. Please submitting to our conferences and journal, including you, of course, our speakers. I mean. And I hope to see you in the next webinar in about 1 month. We have confirmed speakers already, so it will be end of March.
I have a quick question, if you allow me,
Yeah,
for
please.
Professor
Of course,
Abdurrahman.
of course.
Okay. Okay. So the question is, in this multi-agentic system, does he see that there could be denial of or distributed denial of service attack, like what we see in traditional systems?
Thank you, Professor. Basically, yes, distributed denial of service attack is a very common attack for multi-agent system, for sure. And it's a typical application, just like other application. It is just the multi-agentic system architecture is newly introduced, but the existing DDoS attack absolutely applies to multi-agentic system. Yes.
Okay. Thank you.
Thank you for the question. I think it's always interesting to see how all these topics actually rely and pertain consumer electronics. So Matthew clearly explained the relation with mobile, and of course, you illustrated clearly the relation with all these, consumer health-related technologies. So either in hospital or whatever. So once again, thank you and see you next time, hopefully. Bye-bye.
Thank
Bye.
you. Bye.
Bye-bye.